In this lecture, we will discuss linear and non-linear media. So here for most of substances or media, magnetization M is directly proportional to H. So here M is the magnetization and H is the auxiliary field. So or we can write this above question, that is M is equals to chi M H. Suppose this is question number 1. So here chi M is the proportionality constant and this chi M is called the magnetic susceptibility. So here this magnetic susceptibility is a dimensionless quantity and varies from material to material. So here magnetic susceptibility is positive for paramagnetic materials and this is negative for diamagnetic material. So all those material which obey this question, that is a linear question, that is question number 1, that materials are known as linear materials or linear media. So here the materials that obey above question are called a linear media. Further, we know that H, that is auxiliary field, is equals to 1 over mu naught B minus M, or we can write B equal to mu naught H plus m, or we can write mu naught 1 plus m by h and h here. So this m by h is nothing, this is a magnetic susceptibility, so we can write mu naught 1 plus chi m, and here this is a h. Or we can write this mu naught and we can write this is a mu h, this b equals to mu h. Here this mu is equal to mu naught 1 plus chi m, and is known as permeability of a material, known as permeability of the materials. So here we have a special case that is in vacuum, because there is no matter to magnetized. So in vacuum, magnetic susceptibility is equals to 0. So here diamagnetic and paramagnetic materials are the linear material, because they obey the equation, linear equation. So finally here diamagnetic and paramagnetic materials are linear media. Okay, so all the diamagnetic and paramagnetic material are the linear media. So here ferromagnetic are ferromagnetic are non-linear materials. So why it is so? Because here in case of a ferromagnetic materials, suppose this is a ferromagnetic materials, then here we have domains like this. So it means suppose in the first domain the magnetic dipoles are orient in this direction, or in case of this domain, suppose they are orient like this, and here suppose they are orient like this, and in this case suppose they are orient like this. So this is known as domain. It means in each domain all the dipoles are arranged in a particular direction. So here each domain contains billions of dipoles, but it means each domain contains billions of dipoles, and each dipoles will orient in the same direction in a particular domain. But in the material, these domains are randomly oriented, because domains are, although dipoles are arranged in a particular direction in a particular domain, but domains are randomly oriented. Due to this reason, magnetization is equal to 0 in the absence of the magnetic field. So in the absence of magnetic field, the net magnetization is equal to 0. So when we apply the magnetic field, and dipoles and domains, they try to orient in the direction of magnetic field, but no doubt they follow the non-linear behavior, because they are not proposed, the dipoles or we can say magnetization is not proportional to the field. Due to this reason, we call these materials as non-linear materials. Okay. Further, suppose we have a ferromagnetic material, and suppose along x-axis we have a auxiliary field H, and on y-axis suppose we have a magnetization M. Then when and this is a central point, so this point is A. So when we increase the field, then the magnetization goes on increasing initially, and here we get the saturation point. Further, when we reduce the strength of field, then it follows a different path and goes like this. And if we at this point auxiliary field is equals to 0, even then magnetization is not equals to 0. If we further reduce the field in negative direction, then the magnetization again here we have goes to 0 when we apply the negative auxiliary field. If we further increase this, then it moves like this, and if we further reduce the magnetic auxiliary field, then it follow this path. Okay, so here at this point we have a saturation, and also at this point we have a saturation of magnetization. Suppose this point is A, suppose this point is B, this point is C, D, E, F and G. This whole path is A, B, C, D, E, F, G, B. This is known as a hysteresis loop. This total loop is known as hysteresis loop. Sorry, this is hysteresis loop. Okay, I will repeat this. Okay, so this is known as hysteresis loop. Okay, so this A, B, C, D, E, F, G or B, this is the hysteresis loop. Okay, Next point here is, even at when the auxiliary field is equals to 0, at this point at A point magnetization is equals to 0, at C point magnetization is in the positive directions, and here in the F point the magnetization is negative. It simply means here the magnetization has different value at 0 auxiliary field. So although the auxiliary field is equals to 0, even then we have a different magnetization value. That is, at A we have a 0 value, at C we have a positive value, and at F we have a negative value. This shows that the magnetization not only depend upon the magnetic field, but it also depend upon the history or nature of the material. Okay, so in summary, diamagnetic and paramagnetic materials are linear materials, and ferromagnetic materials are non-linear materials. Okay, thank you.